everyone, my name is Jack, and hope you have a great time watching Mommy's video. And for now on, there's going to be a hidden stickman, and comment down below where the stickman was, and you'll get a point, and the points by the end of the year of all the stickmen you found will lead to a piece of candy. Bye.
Didn't know there was going to be a prize for that, but all right, let's jump in here. Lesson 5 is on.
It's gonna be a nice
Yes.
prize, like candy.
Yes, candy. Thank you, Jack. All right, lesson 5 is on graphs of functions and equations. So really, we're gonna keep doing what we've been doing, as you're gonna see in this first video, but now we're gonna graph it, and you're gonna see it's really not that different. This idea of being a function. Okay, so let's start. We can review writing an equation here. The distance that Giselle can run, or Giselle, sorry, is a function of the amount of time she spends writing. She runs 33 miles in 21 minutes. And we're going to assume that she runs at a constant rate. That's important because if it says constant, that means it's going to be a straight line. Okay, constant, we're multiplying the same thing, it's going to increase by the same rate. So write an equation in two variables that represents her distance as a function of time. We should be good at this by now. Distance over time, 3 miles over 21 minutes. I don't care that 21 is bigger than 3. Always put distance over time. Her distance is y, her time is x. So we go 21 times x. I'm sorry, 21 times y equals 3 times x. Since we're always solving for our y, our dependent variable, we're going to divide both sides by 21. And we're going to get y equals. Now I know this seems weird. We want to put 7 because we want to say 21 divided by 3. But we can write this as 3 over 21, or we can reduce it. 3 divided by 3 is 1, and 21 divided by 3 is 7. So we can just divide top and bottom by 7. So here is our linear equation. Remember, y represents miles, and x represents minutes. So in part B here, we want to determine how many miles Giselle can run in 14 minutes, 28 minutes, and 7 minutes. Okay, so notice it says minutes. X is our minutes. So when I plug it into this equation, y is going to equal 1/7 times 14. And I'm going to write it as 14 over 1. And if you go 1 times 14 over 7 times 1, well, that's going to reduce down to 2. Okay, if you need to, 7 goes into itself 1 time, 7 goes into 14 2 times, and we get 2. And remember, y is miles, so that's 2 miles. 28 minutes, that means x equals 28. So I'm going to input that in for x here. So y is going to equal 1/7 times 28. I'm going to raise 28 over 1. 1 and 1 have a common factor of 1. That doesn't help. But 7 and 28 have a common factor of 7. 7 goes into itself 1 time. 7 goes into itself 28, 4 times. And we get y equals 4 miles. And then 7 minutes. So we're going to input that 7 in here into our function. And, well, that's going to cross out to be a whole bunch of 1s, so 1 mile. Okay? All right. So you can see how we've written the equation, and with that equation, we can just pick different amounts of time to figure out how far she'll run. Now we want to get into graphing it. So for the given inputs of the function, a time, the matching output y is the distance she ran in that time. Write the inputs and outputs from part B, as ordered pairs, and then plot them on the coordinate plane. All right, so if we're going to write them as ordered pairs, this one right here will be the ordered pair 14, 2. This one here will be 28, 4. And this one here will be 7, 1. Because again, x value, y value. Input, output. All right, so even though this is not a point on there, if you think about it, if we're comparing how far she runs in number of minutes, if she runs for 0 minutes, then she's gone 0 miles. So I'm going to put a point at 0, 0. You don't have to. It's going to go through there anyway. Okay, so 14, 2. So I go 14 on my x-axis, up 2. 28, 4. I'm going to go to 28 on my x-axis and up 4. And 7, 1. I'm going to go to 7, which is halfway between the 6 and 8 here, and up 1. Okay, and what you notice here is that we have a straight line, which shouldn't be a shock because it was a constant rate. We are anticipating a straight line. Okay, so draw a line through it. And then it says, what do you notice about these points? Okay, well, what do you notice about the points? I noticed that it appears to be linear, right? You kind of know it is, but it's a straight line. So it appears to be linear. Linear means a straight line. And let's think about it here. Would this be a discrete function? Well, if you look, we can break these up to any amount of time. Any amount of time. 30 point, whatever that is. Okay? So if we can break it up to where it's not integers, we can, it runs continuous, we're going to say that this is not discrete. Because we don't just count the minutes, 1, 2, 3, 4. We can say 1.5. We can say 24 1/4. All right, so this is what it looks like for what we've been working on. Graphing it, understanding more about being linear, having a constant, and being not discrete. So let's take a look now at something. There's your little stick man there. At a graph that isn't linear. All right, so if we look at this right here, notice that this isn't going to be linear. Remember in the past we've talked about linear functions are raised to the first power. This is to the second power. Okay, so let's just put our information here on the table. Okay, so what we're going to do is we're going to input this x in here, right? So y is going to equal whatever our x is squared. Well, that's just 0. Okay, or our 1 squared. 1 times 1 is 1. Okay, or our 2 squared. Remember that means, that little 2 means we take 2 and multiply it by itself this many times. So 2 times 2 is 4. 3 squared. 3 times 3 is 9. 4 squared. 4 times 4 is 16. 5 squared. 5 times 5 is 25. 6 squared. 6 times 6 is 36. And we could keep going, which I'm actually going to do that in a second. Okay, but these, remember, are ordered pairs. This is 0, 0. This is 1, 1. This is our input x value of 2 and our output of 4. This is our input 3, 9. You get the idea. So let's put these on the graph. Okay, here's 0, 0. Here is 1, 1. Oh, careful, because I got to notice that goes up by 2s here. 2, 4. 3, 9. Okay, I can look here. 4, 16. 5, 25. And 6, 36. All right, so remember we said we didn't anticipate this to be linear, and it's not. Kind of starts out like it could be, and then you all of a sudden see this curvature happening, right? So what shape does the graph of the points appear to take? Well, it kind of looks like it's curved. Okay, it's a curved line. It's actually, if you kind of look at it, it almost looks like half a U shape. But the word we're looking for here is parabola. Okay, not that you have to worry about using the word parabola right now. If you told me this was a curved shape, that would be fine. But not parabola, parabola. A parabola is a U shape. Okay, and I just want to show you real quick what happens if we put some negative numbers in here. What happens if I put -1? And the reason I want to show you this is you need to be careful. Sometimes in a calculator you can type -1 squared and it will not give you the correct answer. Remember, this means -1 times -1. Negative times negative is a positive. 1 times 1 is 1. Okay, negative 2. That's right, I was saying about a calculator. The calculator doesn't recognize this as a negative 1 unless you put parentheses around here. And I see people make that mistake. They just type it into your calculator, not understanding that our calculator is not reading it as a negative 1, is reading it as the opposite of 1 squared. So if you put negative numbers in parentheses, you're telling the calculator, hey, I want that to be a negative 2. And if you do that, then it's going to come out with the correct answer. All right, and I should have planned this better. Okay, but if I were to extend this out here so I could put those in, here's negative 1, negative 2. You see our points here. At negative 1, we go to 1. At negative 2, we go to 4. Okay, so can you kind of see this U shape? It's coming back up. Okay, that's why it's really a parabola. It is a U shape. Okay. All right, guys, just to finish this up, is this equation a linear equation? Explain. No. We can say it's not a straight line. Or we could say maybe there's no constant. We're not multiplying by the same thing every time. All right, we will pause there and then we'll kind of wrap this up in a second. But again, when we start putting these functions on graphs, they can be linear or they don't have to be. And we're going to be able to tell later on from a graph if whatever's graphed on there is a function or not.